Much like how Unit 7, which had to do with rotational motion, really used physics from throughout the year, kinematics, forces, energy, etc., to describe motion in a new context. We're going to do kind of the same sort of thing here, but now we're going to be looking at specifically simple harmonic motion, which is the subject of Unit 8. And simple harmonic motion seems like a somewhat complicated phrase, but ultimately has to do with the motion of oscillating objects, objects that are oscillating around some equilibrium point. But before we can start going too much into the details of simple harmonic motion, it's important to understand some basic properties of oscillatory motion and for us to be able to write equations for some of these properties when describing these sorts of objects. Now, we've touched on periodic motion back in the first semester, but it would be good to kind of have a bit of a refresher here. So periodic motion is motion that repeats itself in regular time intervals. So beat, 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 beat. It goes through these cycles in a nice formulaic way. Now, periodic motion has two defining characteristics, the first of which is the period, which we abbreviate with a capital T for time, for instance. And it is the amount of time necessary to complete a single cycle. And the units we typically use for that are seconds, because it is a length of time. The other one of these defining characteristics is that of frequency, which we abbreviate with a little f, which is the number of cycles per unit time, and typically that is per second, for instance. Now, that would be units of 1 over s, and that's how we've seen it previously, but there's actually a specific name for this unit, 1 over seconds, and that is hertz, H-E-R-T-Z, which you abbreviate with a capital H, lowercase z. And it's important to remember that these two properties are inverses of each other. The period is equal to 1 over the frequency, and the frequency is equal to 1 over the period. So if you know one, you know both. And additionally, one last thing we want to mention now is that there's really two big examples of periodic motion that we look at in this class. The first of which is uniform circular motion. Objects are going in a circle at a constant rate. But the other form of periodic motion we're going to look at, and the one we're going to be focusing on for this entire unit, is that of simple harmonic motion. So what exactly is simple harmonic motion? That's a very long phrase, so a lot of times when I'm writing on the notes, I'm just going to abbreviate as SHM, just to keep things nice and simple. Well, this is a special case of periodic motion, a special case of this formulaic repeating motion. And it also has a very key defining characteristic, which is that an object that is in simple harmonic motion is subjected to what is known as a restoring force. Now, I want to be careful. A restoring force, much like a centripetal force, for instance, is not a specific force type. It is simply a way to describe other types of forces, whether those are gravity, tension, normal, friction, whatever. It is just a way to describe forces. But a restoring force is, one, directly proportional to the displacement of an object. So in other words, if I have an object that is subjected to a restoring force, if I move it further away, if I increase its displacement, the restoring force gets bigger and bigger and bigger. And additionally, it is always toward this equilibrium point, and therefore it's opposite the direction of displacement. So one, if I have this object at some equilibrium point, if I move this object further and further away, that restoring force gets bigger and bigger and bigger. And additionally, if I'm moving it this direction, the restoring force is always in the opposite direction, back toward this equilibrium point. It allows us to have very stable systems, where if the object moves away from equilibrium, it's going to drift backward. Now, what exactly do we mean by equilibrium? Well, it's much like we've discussed it throughout the year, that equilibrium is a position where the forces are balanced. And if the forces are balanced, that means there is no net force, and therefore there is no acceleration. So at that exact location, acceleration is zero and the net force is zero. But as soon as we move past that equilibrium position, that is going to change. Now, when this object is subjected to a restoring force, that means, typically speaking, it's going to be oscillating back and forth around this equilibrium position. You have an equilibrium, you disturb it a little bit, you move it away from equilibrium, that restoring force is going to pull it back toward equilibrium. You move it away from equilibrium again, restoring force pulls it back toward equilibrium. And it can go back and forth, etc. So how do we describe the motion? of an object in simple harmonic motion. And let's go ahead and start off by giving ourselves a little scenario. Let's say that we have here, for instance, a ball that is attached to a spring at time equals 0, and let's say we've pushed it up so that it does not naturally hang from this point. It actually naturally hangs somewhere down here, and we've pushed it away from this equilibrium position, and then we're going to let go. And if we let go, it's going to go downward to the equilibrium position, and then it's going to go past that point and actually cause the spring to stretch more, and then it's going to start snapping back upward, and then eventually it's going to go back downward, etc. And it's going to take this sort of path through time. So notice this is t equals 0, t equals 0.1 seconds, 0.2 seconds, 0.3, etc., etc., etc. So it's going up, then it goes down, boom, 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 etc. So if we were going to plot the motion of this object, well, let's go ahead and give ourselves a little bit of a graph space here. I'm going to give myself two axes. I've got the y position axis, which I'm going to say is in meters. I did y instead of x because it is vertical. And we'll say this equilibrium position here in the middle, so that would be the point where the ball would just naturally hang. We're going to set as 0. And we're going to say that it initially starts above 0, and then it goes to equilibrium, then it goes below 0, above equilibrium, or to equilibrium, above it, back to equilibrium, and below it. And this is as time progresses. This is time in seconds and the position, vertical position in meters. And what we notice is that this position versus time curve, now notice it's y versus t rather than x versus t, but it's still a position versus time graph, is a sinusoidal curve. Now this word, sinusoidal, seems very fancy, but really all that's telling us it's either a sine or a cosine graph. That's all it is. It's just this waving back and forth sine and cosine motion. And looking at this graph, are there a few things that we can identify? Well, first off, we could say, okay, the period, which would be the time for a single cycle, so that goes from when the ball is at its highest position back to when it returns to its highest position, is t equals, and we just count here, 0.4 seconds. Now, if you want to figure out the period from one of these graphs, we can either do what we did here and go from the crest to the crest of the graph. We could have gone from the trough to the trough of the graph, or if we went from the center, we have to be careful. If we go from the center, it needs to go all the way back to the same spot in the pattern. It returns to the center here, but you notice this is not one full wave. It's going to go up or down, and now it's going to go up and return to its original position. So we have to make sure we're careful with that. But the period is 0.4 seconds. The frequency is just 1 over that period. So if I stick that in my calculator, 1 over 0.4 is 2.5 hertz. Remember, hertz is the unit of frequency, and that's telling me that this ball is going to go through a cycle, specifically 2.5 cycles every second. So by the time this gets to 1 second, it's going to have gone from the top, 1 cycle, 2 cycle, and then down for a half cycle in that 1 second. Lastly, we can identify something known as the amplitude, and the amplitude is the maximum displacement of the object from equilibrium, and the units of that will be in meters. Now we want to be very, very careful. Amplitude is going from the equilibrium point to the maximum, or the equilibrium point to the minimum. We are not going from the maximum to the minimum. That would be 2 times the amplitude, and that's a very common mistake that we see people making. So let's start putting all these pieces together so that we can write an equation for this object in simple harmonic motion. And these equations are going to take the following form. X of t is equal to plus or minus capital A cosine of 2 pi ft. And there are a lot of pieces here, and there's a lot of ways we can fluctuate this. So let's start to go through one piece at a time. Well, first off, the x of t is just telling me that this is the position of the object with respect to time. So this equation is telling me if I stick a time in, if I stick in 0.1 seconds, 0.2 seconds, 0.3 seconds, whatever, it will tell me, once I solve it, the position of that object at that particular moment in time. Now, I did x of t here. You could have done y of t if you wanted to do vertical. Really doesn't matter. But you've got x of t, and then for this time here at t, now if we were trying to solve for a specific position, we would put an exact value in there. But if we're just writing the equation, we're going to leave the t alone, because the t is the variable that we're going to input into the equation to find the specific position. So we've got those first two pieces. The next thing we have is we have the amplitude, which is just in meters if it is in, for instance, position. We have the frequency right here in this parentheses part, and that frequency will be in hertz. And a lot of times you'll see this slightly rewritten. You'll see the part in parentheses, rather than being 2 pi ft, you'll see it as 2 pi little t over big T, keeping in mind that frequency is equal to 1 over the period, so those would be the exact same thing. Additionally, though, we also have this plus or minus cosine. We can really put in different sinusoidal curves here. It can be a positive cosine, a negative cosine, a positive sine, a negative sine. It depends on what the initial position of the object was in its oscillation, and we'll talk more about that in a second. But all of the equations we get should look somewhat like this. Some things are going to be changed, but they should be of this form. And additionally, if we expand this to a v versus t, so a velocity versus time, or an acceleration versus time equations, they're actually going to be of the same form. Now, they're not going to be identical. So, for instance, an x versus t graph and then the v versus t graph for that same object, they are not going to be the same equation, but they are going to be similar. They are still going to be sinusoidal in shape. And specifically, this part in parentheses here will be exactly the same for each one. Now, the big difference, though, between these, between the position, velocity, and acceleration graphs is, one, that they're all going to be a little bit offset from each other, and we're going to discuss that much more in class. And two, that rather than having the amplitude out here in front, which remember that's the maximum displacement, we would replace this with either the maximum velocity or the maximum acceleration, depending on if we're doing a v of t or an a of t equation. Now, one last thing I want to mention, this whole part in parentheses, you might be thinking, where did this 2 pi ft come from? Hold on to that. We're also going to discuss that in class so it becomes a little more clear. So, for instance, returning to this previous picture we already drew, we already identified quite a few things here. And I'm going to go ahead and say that the amplitude, just for the sake of this example, we'll go ahead and say it was equal to 0.1 meters or 10 centimeters. So that is how much it goes above the equilibrium. That would be how much it stretches down below the equilibrium as well. Now, if we're going to write an equation for the motion of this object, we have to do a couple of different things. One, we need to identify the particular type of sinusoidal curve that it is. And two, we need to determine the amplitude, the period, and the frequency, which we already did for this particular situation. Now, as it comes to the sinusoidal curve here, well, a lot of you will know from your pre-cal class, you can look at this and go, oh, this is a positive cosine graph. So this is specifically positive cosine, and then if I'm going to write my equation, I would do it of the form just described. I would do y of t here rather than x of t, because it's vertical, is equal to the amplitude, which was 0.1 meters. It is a positive cosine, so I'm going to leave it as positive cos. 2 pi, the frequency was 2.5 hertz times t. Or I could have written this similarly in the exact same format, except instead of doing 2.5 hertz multiplied here, I divided by 0.4 seconds, which is the period. And we'll see that that gives me the same equation either way. Because now to simplify this a little bit, I'm just going to multiply 2 by 2.5 or divide 2 by 0.4. We'll get the same answer. And we get a final equation of y of t is equal to 0.1 meters cosine of 5 pi t. That is the encapsulated position equation for this particular object. Now, if you're not in pre-cal, or maybe you just don't quite remember, you might be thinking, where the heck did we get the positive cosine from? How did I know that was a positive cosine graph? There are 4 sinusoidal curves you're going to have to need to know. You need to know them specifically and be able to identify them by sight. And they are positive and negative cosine and positive and negative sine. Well, first off, let's go through them one at a time. The positive cosine graph is always going to start above the axis, because we're only going to be looking at situations where we're either starting at a maximum, a minimum, or at 0. We're not going to start at some weird middle point. So this is going to be a positive cosine graph if it has a y-intercept above that axis. On the flip side, a negative cosine graph starts below this axis. The sine graphs can be a little more confusing, because if you notice, these are both sine graphs and they both start at 0, but what we can look at is the initial slope. If the initial slope of the graph is positive, that is a positive sine graph. And if the initial slope of the graph is negative, that is a negative sine graph. So in these 4, we need to be able to identify pretty quickly and pretty accurately. So let's go ahead and just do one practice example together. Let's say I've got this acceleration versus time graph here, and the time is in seconds, the acceleration is meters per second squared, and we want to know what is the equation for the acceleration of this object with this specific a versus t graph. Now, if you feel confident in this, go ahead and give it a shot, come back, and we'll see how you do, but otherwise, I'm going to start going through it here. Now, remember, even though this is an a versus t graph, it's going to have a similar form to an x versus t equation. They're going to still be sinusoidal. They're going to be not identical, but they are going to be identical in form. So the first thing I need to do is I need to identify what sort of sinusoidal graph is this. Is it a positive cosine, positive sine, negative sine? Okay, well the graph starts at 0, and additionally it starts with a negative slope, so that tells me this is in fact a negative sine graph. The next thing I need to be able to do is I need to say, okay, I need to find the amplitude, the period, and the frequency. All right, well looking at this graph, the amplitude appears to go from 0 to this maximum point here, so the amplitude is 0.4 meters per second squared, so that's from equilibrium to the maximum. It's the same thing to the minimum. And the period, now notice I started here, and I went all the way through a complete cycle. So I went both up and down. I didn't just stop here. And that is a time length of 2 seconds. And 1 over that for the frequency would be 0.5 hertz. AKA, when 1 second has passed, only half of a cycle has occurred, which definitely is what I see here. All right, so now that I have those, let's start forming these into equations. So I have A of t, rather than x of t, is equal to 0.4 meters per second squared times, okay, this is a negative sine function, 2 pi, and for the frequency I could put 0.5 hertz times t here. Or I could have done the exact same thing, but rather than multiplied by the frequency, I could have divided by the period. Either way, 2 times 0.5 is 1, 2 divided by 2 is 1, so we should get the same answer either way. And I'm going to get a final answer of A of t is equal to negative 0.4 meters per second squared sine pi of t. That is a specific equation for this acceleration versus time sinusoidal curve. All right, so what are our main takeaways for describing oscillations? Well, one, can we remember what periodic motion is and determine the period and frequency of any sort of periodic motion, keeping in mind they're inverses of each other, and also keeping in mind that frequency is units of hertz, or 1 over seconds. Can we describe simple harmonic motion as oscillatory motion around an equilibrium position and its defining characteristic that the object is subjected to a restoring force that is directly proportional but opposite in direction to its displacement from equilibrium? Can we identify properties of simple harmonic motion by analyzing an x versus t, v versus t, or a versus t graph? AKA, could we figure out its amplitude, its maximum velocity, its maximum acceleration? Can we figure out its period, its frequency, etc.? And can we write sinusoidal equations for the position, velocity, and acceleration of objects that are in simple harmonic motion, just like we've now done a couple of times?